All right, let's dive in. Today, we're going to pull back the curtain on something called object-oriented programming, or OOP for short. It's the powerhouse philosophy behind pretty much all the software you use every single day. And we're about to break down exactly how it all works.
So have you ever thought about how developers build these enormous apps with millions of lines of code? I mean, without some kind of brilliant strategy, it would just turn into what we call spaghetti code, a complete, tangled nightmare that's impossible to fix or update. Well, there is a solution to all that chaos, and that's what we're here to talk about.
And that solution is a way of thinking called object-oriented programming. And look, it's not just a bunch of tools or commands, it's a whole different way of looking at code that brings order and, frankly, sanity to the complex world of software development.
At its very core, OOP is all about modeling the real world. So instead of writing these long procedural lists of instructions, we create these little self-contained things called objects. And just like objects in the real world, they have their own data and their own behaviors, all bundled together. Now, to really get a grip on OOP, you have to start with the most fundamental idea of all, the relationship between a blueprint, which we call a class, and the actual thing you build from it, which we call an object.
Let's make this super simple. Think of a class as the architectural blueprint for a car. It defines all the general stuff, right? Like it's going to have a color, a model, and things it can do, like drive. The object, on the other hand, is the actual car built from that blueprint, the one sitting in your driveway with a specific color, like red, and a specific model.
And here's what that blueprint actually looks like in code. We define a class called car. Inside, we have string color and string model. You can think of these as empty labels or attributes, just waiting for real values. And that display thing, that's a behavior or a method that defines an action the car can actually perform.
Okay, now for the fun part. We use that blueprint to create a real object. This line, car, my car, equals new car, is like the factory building the actual car. Then we use that little dot to give it specific details. MyCar.color becomes red, and MyCarModel becomes sedan. Just like that, we've brought the blueprint to life.
So once we know how to make blueprints, we can start building on top of them. And this leads us to our next amazing concept, inheritance. It's basically a massive efficiency hack for writing better code faster.
The whole idea here is just common sense. Why reinvent the wheel? If you've already written and tested code for a general thing, why would you rewrite it all from scratch for something more specific? Inheritance lets a new class just absorb all the features of an existing one. It's all about reusing your work.
Let's start with a really general blueprint, our base class. We'll create a vehicle class, and we'll say that any vehicle we make has a brand and a honk method. This gives us a solid common foundation to build on.
And now we can create a more specific class. Let's say bike. By using this special keyword extends, we're literally telling the program, hey, a bike is a type of vehicle. And boom, instantly our bike class gets the brand attribute and the honk method, and we didn't have to write a single extra line of code for it.
And here's the proof. Even though we never ever defined a honk method inside our bike class, we can call it, and it just works. That is code reusability in action, and it is a beautiful thing.
Okay, this next concept, polymorphism. It sounds super complicated, I know, but trust me, the idea behind it is actually incredibly elegant. It's all about writing flexible, adaptable code that can handle different situations without breaking a sweat.
Just think about the action make a sound. What that actually means completely depends on what is making the sound, right? An animal, a dog, a cat, they all make a sound, but they do it in totally different ways. Polymorphism lets our code understand and reflect that exact reality.
So we can start with a general animal class, and it can have a default sound method. It's generic, which is exactly what we want at this level.
But now, here's the cool part. When we create a dog class that inherits from animal, we can actually override the original sound method with its own specific version. So now, the exact same method name produces a completely different result, a bark.
And of course, we can do the exact same thing for a cat. This is the magic of polymorphism. We can tell any animal object to make a sound, and the program automatically knows whether it should bark or meow. This makes your code so much more dynamic and smart.
Let's finish up with two principles that are absolutely essential for building professional, secure, and maintainable software. Seriously, this is the stuff that separates the hobbyist code from the real enterprise-grade systems.
Think of encapsulation as putting your object's important data inside a protective bubble or a capsule. You don't want other parts of your program just reaching in and changing critical information whenever they feel like it. Instead, you create specific, controlled, public methods to interact with that data safely.
And you can see it right here in the code. Notice that little word private next to the name variable? That makes it completely off-limits to anything outside the object. The only way to read or change that name is by going through the public methods getName and setName. This gives the object total control over its own data.
And finally, we have abstraction. Honestly, this is all about working on a need-to-know basis. When you drive a car, you just need the steering wheel, the gas pedal, and the brake. You don't need to know about the fuel injection system or the timing belt. Abstraction does the same thing in code. It hides all the messy, complex details and just gives the user a simple, clean interface to work with.
So we've talked about classes, objects, inheritance, all this stuff. But why go through all this trouble? Let's bring it all together and see how these ideas solve that spaghetti code problem we started with.
When you get right down to it, all these principles give us huge advantages. OOP gives us modularity, so we can break down massive problems into small, manageable pieces. Inheritance gives us reusability, which saves a ton of time and effort, and things like encapsulation make our code way easier to maintain and protect our data, keeping our programs stable and secure. It's a win-win-win. By thinking in terms of objects, we can model pretty much anything, from a complex banking system to the characters in a video game. These principles aren't just theory, they are the literal building blocks of almost all modern software. So the only question left is, what will you build with them?